Welcome to this deep dive, where we take your sources and hunt for the gold.
And today, our source is a big one, RFC 4253.
Right, the Secure Shell Transport Layer Protocol, SSH.
Exactly. Think about when you need to securely connect to another computer, maybe way across the internet.
Login, transfer files, that kind of thing.
Precisely. SSH is pretty much the standard tool for that. And this RFC, it lays out the groundwork, the secure channel that makes it all possible. It's fundamental.
Okay, so our mission today is to unpack how it builds that secure connection. We'll pull out the really interesting bits from this technical standard.
Let's do it. So the RFC says SSH usually runs over TCP/IP, typically port 22.
The standard SSH port.
Right. And the very, very first thing that happens, the client and server, they just swap these simple identification strings.
Like saying hello.
Kinda. More like shouting their version number across the void, SSH 2.0, and maybe their software name. It's just to check, hey, do we speak the same basic SSH language?
Makes sense? Quick compatibility check.
Yep. And right after that, they switch gears immediately. They go to a binary packet protocol.
Okay, binary packets. And the RFC gets specific about these.
Oh, yeah.
Yeah.
Very specific. And the structure itself tells you a lot about the security goals.
How so?
Well, each packet has a length field first, then a padding length field, then the actual data, the payload, and then variable length padding, followed by a message authentication count, or MAC.
Wait, variable length padding. Why variable? And the RFC says minimum 4 bytes, right? Up to 255.
Exactly. It's not just there to make the packet a certain size. That variability is key.
Why? What does it do?
It's actually a defense against traffic analysis. By adding a random amount of padding, it makes it much harder for someone snooping on the connection to figure out the size of the real data being sent.
So they can't guess what you're doing based on packet size. Like typing versus file transfer.
Precisely. It obscures those patterns. It's a really clever bit of security baked right into the packet structure.
That is clever. Okay, so they've got the secure packet format. How do they actually set up the encryption?
Right, this is the core part, the key exchange. So both sides send a message, basically a list.
A list of what?
All the crypto algorithms they support. Key exchange methods, encryption ciphers, MAC algorithms, compression, the works.
Yeah.
And they list them in order of preference.
So they're negotiating, like, I prefer this strong cipher, do you have it?
Exactly. The goal is to find the first algorithm on the client's list that the server also supports. For each category, encryption, integrity, and so on. They agree on the strongest common set.
Okay, negotiation makes sense. And how does the key exchange itself work? You mentioned Diffie-Hellman.
Yeah, that's a common one described. And this is where the real magic happens. Using some clever math, they can both arrive at the same secret key, let's call it K.
Without ever actually sending that key over the potentially insecure line.
That's the whole point. They generate it together without transmitting it directly. They also calculate something called an exchange hash, H. It's like a summary of all the key exchange messages.
And that H becomes the session ID, the unique identifier for this whole connection.
Bingo. That first H is the session ID. And then using that shared secret K and the hash H, they derive all the other keys they need.
Other keys, like more than one.
Oh, yes. They need separate keys for encrypting data from client to server, server to client, and critically, separate keys for calculating the MCs in each direction, too. The RFC specifies exactly how to derive these from K and H.
Wow, okay. So, negotiate algorithms, create a shared secret K and hash H, derive all the working keys. How do they, flip the switch to start using them?
Simple message, SSH MSG new keys. Each side sends one.
And this message itself isn't encrypted yet?
Correct. It's sent using the old unencrypted method. But the moment you receive SSH MSG new keys, you immediately start using the newly negotiated keys and algorithms to process incoming data.
And after you send it?
After you send it, you start using the new keys and algorithms for sending data. It's a synchronized switch.
Got it. And that MAC on every packet, that's the integrity check, making sure nothing got flipped or changed.
Exactly that. It's calculated using the specific integrity key for that direction, a packet sequence number which goes up by 1 for every single packet, and the actual packet payload before encryption.
So if even one bit changes in transit?
The receiver calculates the MAC on what they received. If it doesn't match the MAC that was sent with the packet, they know it's been tampered with, discarded. It's a constant integrity check.
Okay, wrapping up then. We've really dug into RFC 4253, the SSH Transport Layer.
Yeah, we saw the whole process, that initial handshake, the clever packet structure with padding to resist traffic analysis.
Then the negotiation of algorithms, the key exchange like Diffie-Hellman to create that shared secret key and session IDH without exposing the key.
And finally, deriving all the necessary encryption and integrity keys and using those MFCs on every single packet. It's quite a layered approach.
And something you mentioned that's really interesting, this layer is flexible, right? It lets you negotiate modern, strong algorithms.
Definitely. But the RFC also had to mandate support for some older stuff like 3DES back in the day, just to ensure things could still connect. Backward compatibility.
Even if those older methods weren't ideal anymore.
Right. It shows the balancing act. You want strong security, but you also need things to, well, work together across the internet.
So it really highlights the engineering challenge, building trust online, packet by packet, while managing this constant evolution of threats and algorithms.
Absolutely. Which leads to a final thought for you to mull over.
Yeah.
How do we keep pushing essential protocols like SSH forward, making them stronger against new attacks when there's always this anchor of needing to stay compatible with older, potentially less secure systems still out there? It's a constant tension in internet infrastructure. Something to think about.